you to the IRIS Transportable Array Working Group webinar. I think this is, I just wanted to point out that one of the data products that IRIS has worked on from our data management system is doing a standard back projection approach, which you'll learn about today, using data from several different array data sets. And so I just wanted to show the web pages for that. We have one on the IRIS data management system page, which is provides some information on what these are good for, what they're not good for, explains how the data is selected and processed, and then gives a couple examples of what you would look for in results from that. And then you can go to a page where these are actually available for download from all the earthquakes that are within the criteria for constructing these. And so there's a whole list of events. These are just usually a couple days behind when the actual event occurred. And then I selected the recent earthquake in Guerrero, Mexico, and I just wanted to play this real quick, which shows the actual back projection result. So after the talk today, if you're interested in seeing what's available, this is sort of a standard reference product that the data management system has put together. I would encourage you to go to these two pages. You can see the URL at the top here. And if you just go to Google and search for IRIS back projection, it'll be, I think, the first hit. So with that, I'll turn it over to Vera to introduce Eric.
Hi, everyone. Thanks for tuning in today. Our speaker today is Eric Kiser, and Eric got his bachelor's in geology at the University of Illinois. He's now a grad student at Harvard and works with Miyake Ishii. And today he will present the source complexities of recent megathrust earthquakes as imaged by the back projection method. Eric?
All right. Thank you very much for that introduction. Can you see my screen out there?
Yeah.
Okay.
Looks good.
All right. So yeah, I'd like to start by thanking the IRIS Transportable Array Working Group for inviting me to speak today. I'd also like to thank all of you in the audience who took an hour out of your day to listen to me talk. This is the first time I've presented in this webinar format, so I'll try to keep things moving at a good pace and hopefully keep all of you interested in the talk. So as the title suggests, today I'm going to be showing you some of our back projection results from some of the recent megathrust earthquakes that have occurred. Having an issue here. Hang on one second. Okay, so I'll start out the talk by giving you a little bit of motivation into why back projection was originally developed and why it's useful for studying earthquake sources. I'll then kind of give a brief description of the method and also just briefly touch on some of the different processing steps that can be used within the method, depending on what aspects of the rupture you're interested in. And then I'll move on to the results. So I'm going to show results from the 2010 magnitude 8.8 Mali, Chile earthquake, as well as the recent 2011 magnitude 9 Tohoku, Japan earthquake. And as you can see here, I'm going to touch on similar aspects of each rupture. So I'm going to be talking about rupture segmentation, dynamic triggering, and also frequency dependence for these two ruptures. And hopefully by concentrating on similar aspects of each rupture, I'll be able to give a good comparison between the two earthquakes and hopefully show you where they're similar and where they are different.
Hey, Eric, can I interrupt you for just 1 second?
Yes.
Yeah, I forgot to mention this when we officially got started, but as Eric is presenting, if anyone out there has any questions, please type them into the window that's on the GoToMeeting control panel, and after he's finished, we'll have the sort of standard back and forth question and answers that would be in a colloquium, and I'll just relay your questions to Eric. Okay, go ahead, Eric, sorry.
All right, yeah, no problem. Okay, so to provide some motivation as to why back projection was first developed and is becoming more and more popular today, I'm going to focus on the source region of the 2010 Mali, Chile earthquake. So what's being plotted here with the black star, this is the epicenter of that event. The yellow dots, these are the aftershocks of that event. These red triangles, these are a few GPS stations that recorded the displacement of that event, and then finally these white lines, these are showing the approximate latitudinal extents of earthquakes that have occurred in this region over the past 200 years or so. So this isn't a very detailed list, but it kind of gives you an idea of what the past seismicity looked like in this region. So you had this extremely large 1960 event to the south of this aftershock distribution. You had these two events to the north of, or in the northern part of this aftershock distribution in 1985 and 1971. And then right around the epicenter and slightly north of the epicenter, or sorry, slightly south of the epicenter, you have this 1835 event. So the fact that this region around the epicenter and slightly south of the epicenter hasn't ruptured for nearly 175 years definitely got the attention of many seismologists and other scientists, and therefore this region before this event was labeled a seismic gap, where there was this high potential, or thought to be this high potential, for a large rupture to occur here. So we can get a general idea of the rupture characteristics of this earthquake by just looking at this aftershock distribution. For example, if you just look at the length of the aftershock distribution, you may conclude that you had a bilateral rupture coming off the epicenter here, and that the rupture length was about 650 kilometers. You may also conclude that this seismic gap was indeed filled, because you have these aftershocks within that region. However, that's a very general overview of what you can infer, and a better approach and a more detailed approach is to actually model slip for these very large events. So this can give you a very detailed spatial temporal distribution of where slip actually occurred, and that can help you whenever you're trying to determine where you need to send resources directly following a large event, and also where you may expect future large events in this region. So this is a very interesting point for this region, because you have this seismic gap. So here's one slip model. It's a preliminary slip model that was put out by Caltech Group for this earthquake. What's being plotted with the colors here are the magnitudes of slip. The red star, this is just the epicenter of the event. So what you can see from this model is that you had highest slip north of the epicenter with maximum slip of about 9 meters. You can also see that this model doesn't have significant slip south of the epicenter in the seismic gap. So based upon this model, you may conclude that there may be a large there's still the potential for a large earthquake near and south of the epicenter of this event. If you instead look at this slip model put out by UC Santa Barbara, you see a much different picture. So here they have highest slip south of the epicenter, which peaks out at about 12.5 meters. And from this slip model, you would say, yes, the seismic gap did rupture, and therefore perhaps we shouldn't expect another large earthquake in the near future. So as I said, these were both preliminary results just put on the web, and later on in the talk I'll probably maybe argue that both results are actually right, but I think these two results illustrate the point that whenever you do these slip models, it's very common that you have to put constraints on your rupture in order to stabilize the inversion for slip. So Some of these constraints may be the directions at which you allow rupture to propagate, or even the velocity at which you allow rupture to propagate. And it turns out that changes or differences in these subjective decisions in terms of the constraints on rupture can lead to very different slip distributions. So really this was the motivation for back projection, and why it's starting to be used quite a bit, is because we wanted, or they wanted, to come up with a method that would allow you to put some basic estimates on the rupture parameters of an earthquake without having to apply these a priori constraints to the rupture. So that leads me to the back projection method. The basic idea of back projection is very simple. You start out, you have to have, well, you don't have to, but the method works best if you have a dense array of seismic stations, shown here with the black dots. And whenever an earthquake occurs, this seismic array of stations will record the wavefront from that earthquake. Now this wavefront will have a certain curvature and orientation to it, and that curvature and orientation will depend upon the source location of the earthquake. So what you can do is you can use that information about the wavefront to actually locate the source of the wavefront. So we do what we call back project the energy back to the source location and determine the source of that wavefront, or the source of energy. Now for large ruptures, the source of energy, well, I should say for large ruptures, the curvatures and orientations of wavefronts that are recorded in your seismic array will change through time. And that's indicating that the source is changing. So you can once again use that new information about a later wavefront to determine your new source location. And in this way, for these very large earthquakes, you can image the propagation of rupture through time. So that was just a very general overview. I'm going to show you a synthetic test here just to kind of illustrate how this process actually works. So to illustrate this, what I've done is I've set up a point source at this red star here. This just happens to be the epicenter of the 2010 Chile event. From this point source, we generate synthetic seismograms at this set of TA stations. And this is showing those seismograms. So this is travel time versus distance from the epicenter. So whenever I said before that we back project energy to the source, what that really means is that we calculate the theoretical travel times between this point and this group of stations, and then we basically time shift the seismograms recorded at those stations by that theoretical travel time. So whenever you do that for this group of stations to this point, this is what you get when you look at the time-shifted seismogram. So you see the wavelets line up very nice. And then what we do, we just add them together or stack them to produce this stack. So you can see on this stack you have a very high amplitude peak showing that this is the source of your energy, which is not surprising because I told you that to begin this synthetic test. But to further illustrate this process, let's look at a different source location, or possible source location. So now we'll look at this blue star, which you know is not the source of energy. So we once again calculate the travel times from this blue star to each one of these stations, and then time shift these synthetic seismograms by that time. Whenever you do that, you see now the wavelets don't align as well, and whenever you add them together, you get a very low amplitude, kind of diffuse stack, indicating this is not the source of energy. So you can do this for a large grid of possible source locations, which are shown here with the black dots. I'm just pulling out a few of the stacks from a few of these source locations where you have very low amplitude stacks to the north and south of the point source, and then, as I showed before, at the point source you have this very high amplitude stack. And one way of kind of visualizing these stacks is just to integrate the squared amplitude of the stacks and then plot that value at each grid point. And whenever you do that for this point source, this is what you see, where warm colors are indicating very high amplitude stacks, and the blue, colder colors are showing low amplitude stacks. So this kind of illustrated the back projection method, and it showed that we can image a point source, but as I said before, we want to image ruptures, large ruptures. And one of the problems with that, or one of the complexities, is that you commonly have multiple sources of energy for these large ruptures, and these different sources of energy commonly have much different amplitudes. So to kind of show how that can make it difficult to actually look at the details of the rupture, I'm going to show you a second synthetic test really quick here. So for this synthetic test, we actually have 3 point sources shown here with the white stars. The only difference between the 3 point sources is that the point source in the middle has an amplitude which is 10 times larger the point sources to the north and south. So whenever you apply the back projection method I described earlier, where you just add seismograms together, this is the back projection image you get. So you can see from this image that we're imaging this very high amplitude point source very well, but for the point sources to the north and south, we don't see a signal at all. And what's going on here is that the smearing of energy from the high amplitude middle point source is basically dominating the signal from those smaller point sources. So this result, and the method I described to you earlier, is referred to as linear stacking, where you just add the seismograms together. However, because of problems like this one I'm showing you, a lot of groups have developed additional processing steps or modified processing steps within their back projection analyses to try to basically reduce the dependence of the back projection results on amplitude information. So there's a long list of these different processing steps you can use. A few you may see in the literature is in-through stacking is very common. The music technique is very common, and what I'm going to be using for this talk is the coherency function. Now I don't have time to really discuss what we do for the coherency function, but the important point to note for this talk is that it's reducing the dependence on amplitude information, so that whenever you do the back projection analysis using this processing step for these 3 point sources, this is the image you get. So you see we now image all 3 point sources, and they have approximately the same amplitude for all 3 point sources. So using the coherency function, you can better constrain the spatial and temporal distribution of energy release. However, you can see you have no amplitude information, so if you're interested in that aspect of the rupture, then you want to go back to linear stacking. So I showed you these 2 different approaches because I'm going to be using both throughout this talk, and I'll try to make it clear as to what result I'm showing and why I'm showing that result. So that hopefully that gave you some idea of how the back projection method works. I'm going to move on to results now, and I'm actually going to come back to the source region of the 2010 Mali, Chile earthquake. So as we discussed before, you have this very large aftershock distribution. You have this seismic gap. It's interesting as to whether the rupture actually occurred within that seismic gap or not. And you have some disagreement between different slip models for this earthquake. So this is the data we use for this earthquake. The orange triangles, these are the transportable array stations we use. Pretty much this is the only data we actually use for this earthquake that I'll show in this talk. We also use full or the FNet and HiNet stations from Japan, but those are basically used to confirm the results that we see using the TA data. And just to kind of ease you into these results again, I'm going to go back to this gridded image around the epicenter of the 2010 Chile earthquake. So the black dots, these are the possible source locations. So this is the grid that we set up. And what's being shown on the right here, these are a few samples of the stacks that are generated at these different grid points. So you can see it's a lot more complex than the point sources I showed you earlier. So as I discussed earlier, you can integrate these entire stacks and try to get an idea of the energy distribution from that perspective. Another way you can look at the ruptures or visualize the ruptures is to look at the amplitudes of these stacks at different time slices. So to demonstrate that, we'll first look at the stacks at 45 seconds into the rupture. So just by looking at these three stacks, you can see the stacks to the north and to the south have very low amplitude results at this time, whereas the stack near the epicenter or at the epicenter has the highest amplitude at this time. So if you plot these amplitudes at this time for all the grid points, this is the image you get. So you can see you have the highest energy release close to the epicenter and slightly north to the epicenter at 45 seconds. If we now move to a later part of the rupture, say 90 seconds, you can see that the energy distribution has changed dramatically. Now, well, you can just see it from the stacks. You have this very high amplitude for this northern stack, whereas in the middle, near the epicenter and to the south, you have very low amplitude stacks, indicating that, as this is showing, the rupture is propagated to the north. So you can repeat this procedure for many different times and generate many different images and then put those images together to create a movie, which probably does the best job of actually visualizing this rupture. So this will be the rupture propagation for the 2010 Chile event, and I'll just note here and come back to this later that we are using TA data and we're filtering it between 1 and 5 hertz, so very high frequencies for this initial back projection result. So what you'll see in this movie is energy starts at the epicenter, as you may expect. It then moves slightly to the north, and then at about between 65 and 75 seconds, you really see this energy release pick up very far to the north, and it seems to peak out at about 90 seconds or so. So I'll just let this play again. Okay, so here's the energy distribution for this entire event. As I said before, you have this dominant northern rupture. Turns out if you actually track the energy through time for this dominant northern rupture, you get a rupture velocity of 2.9 kilometers per second. In total, you have a rupture length of about 600 to 650 kilometers, and that's including this very low amplitude pulse of energy to the south. So that agrees pretty well with the aftershock distribution I mentioned before, and also as you saw from the movie, the energy, the energy dies out at about 220 seconds. So from that initial movie, it was pretty difficult to see both the initial parts of the rupture as well as the southern parts of the rupture, so I'm going to focus on those two aspects of this earthquake now. So we'll zoom in on this region near the epicenter, and this is what you'll notice, a rescaling of the energy release. That's just so you can visualize things a little better. So you'll see from this movie kind of what you saw in the original movie. Things or energy starts at the epicenter. The rupture moves to the northeast. This northeast movement of the rupture has a rupture velocity of 2.2 kilometers per second. The rupture length is about 100 kilometers, and the duration of this initial rupture is 45 seconds. So the reason why I cut this off at 45 seconds is because you may have noticed it already. At 45 seconds, you have a jump in this rupture from down dip to further up dip. You'll see it coming up here. So high amplitude energy release, and then right there, you see this jump in the rupture. So this may look like a very small feature to you, depending on how many back projection results you've looked at. But I'll come back to this later. We think this is actually a significant feature of this earthquake. Okay, so as I mentioned earlier, it's also very difficult to visualize the southern aspect of this rupture from that original movie I showed you. So we're going to focus in on the southern part of the rupture. It's difficult to actually see this rupture propagating to the south at the beginning of the earthquake, so we were kind of forced to start this at 60 seconds after the epicentral time. So here's that movie. So you see this pulse of energy migrating to the south. At about 75 seconds here, it starts to peak out, and then that peak, or that pulse of energy release, basically the interesting thing about it, between 75 and maybe 95 seconds or so, maybe 70 to 90 seconds, it doesn't really move at all. So you have this pulse of energy that lasts about 20 seconds, and we estimate an average rupture velocity of about 0.8 kilometers per second. And it's difficult to tell, but it seems that the overall movement is slightly to the west, actually, for this last pulse of energy. Okay, so to summarize this event, as I mentioned in the beginning of the talk, one aspect of both this earthquake and the Japan earthquake that I'm going to focus on is rupture segmentation. So the way we define that is by different segments that have their own rupture directions as well as their own rupture velocities. So we have 3 segments for this earthquake. We have this initial segment which ruptured to the northeast at a rupture velocity of 2.2 kilometers per second. The second segment, which had the highest amplitude and the highest rupture velocity at 2.9 kilometers per second. And then this very weak segment to the south, which was had a very slow rupture velocity. And then in addition to that, as I said before, we think we have this jump in the rupture. Now it should be noted that if you look at just the first month of aftershocks for this event, you do see a small break in the aftershock distribution right where we image this jump in the rupture. Okay, so those were the back projection results using data filtered between 1 and 5 hertz. You can also do the back projection results for lower frequencies. The main trade-off here is that as you go to lower frequencies, you begin to lose resolution, but you can also see some interesting things about the rupture by doing this. So next I'm going to show you the back projection results using data filtered between 0.5 and 1 hertz, so slightly lower frequencies. So here's just this movie again. What you'll notice from this movie probably is that the rupture doesn't look that much different than the high frequency case. You have this dominant northern rupture that peaks out at about 90 seconds. It's very similar to what I've already shown you. However, because these two frequencies exhibit very similar rupture properties, we thought we'd compare the spatial temporal distribution of energy release for their main feature, which is this strong northern rupture. And whenever we do that, we see something very interesting. So what's being plotted here on the y-axis, this is latitude. On the x-axis, this is time. The black dots, these are the latitudes and times of energy release for the high frequency result. The red squares are for the low frequency result. And what you can see here is that for the high frequency energy is preceding the low frequency energy in the direction of rupture, which is to the north. You can also see that in this movie. So what I'll be showing you is with the background colors, that will be the low frequency result, and with the white contours, that's the high frequency result. And this is just for the northern rupture, so you can see we're picking it up at 68 seconds into the rupture here. So you see the high frequency energy begins first. Here comes the low frequency energy, and you can see it's actually following the high frequency energy. So I'll let this play again. So in the direction of rupture, northeast, high frequency energy is preceding lower frequency energy. Another aspect of this rupture that we didn't really focus on whenever we wrote this study up was that the lower frequency energy is up dip of the high frequency energy. And that becomes important in comparing it to the Japan earthquake, which happened after the study. So basically, in terms of the energy the high frequency energy preceding the lower frequency energy, we interpret this as breaking of the fault, which is preceding kind of the smoother slip that follows. Okay, so you get basically the same picture as you go to lower and lower frequencies, where the lower the frequency, the farther behind it lags the high frequency result. And you get that same picture of the rupture until you get to a frequency range of 0.05 to 1 hertz, or sorry, to 0.1 hertz. And at that time, you see actually a very interesting thing. You see a dramatic shift in the rupture behavior of this earthquake. So that's being shown here. On the y-axis, you have latitude. On the x-axis, you have amplitude. So this is just showing you the latitudinal distribution of energy release. With the red line, this is the high frequency result. So you see it peaks out in the northern or north of the epicenter, which is shown here with the blue line. And for the black line, this is the very low frequency result. So you can see this peaks out south of the epicenter. So basically, you image two completely different rupture behaviors depending on what frequency of energy you're looking at. And this may be suggesting something about the material properties between this northern and southern patch, with, I guess, the most obvious interpretation being perhaps you had slower slip for the southern patch, which would produce more low-frequency energy compared to the northern patch. Okay, so this is the overview of this earthquake. This is kind of the story we told. The paper we wrote about this earthquake, you have this distinction between the northern and southern segment in terms of frequency content, and you also have this very complex rupture as imaged with high-frequency data with rupture segmentation and this jump in the rupture. So I'm going to focus on this jump in the rupture a little bit more now before moving on to the Japan earthquake. So kind of the epilogue to that study occurred about a week ago now. So I'm going to just go back to an overview of the source region for this 2010 earthquake. Once again, the white star is the epicenter. The red dots, these are the aftershock locations for this 2 years of aftershocks. And what's being plotted with this CMT solutions are earthquakes that had magnitudes of 7 or greater. So you can see one of these events is in the outer rise. That's the largest event, 7.4. One of the events is kind of in the northern part of the rupture. It actually has a focal mechanism which is opposite of what you would think of if it occurred on the interface. It's also slightly shallower than other events that would occur on the interface. So I think it's a strong possibility this is actually occurring in the overriding plate. And then about a year after the main shock, you had this aftershock to the south, which is right at the southern border of this aftershock distribution. And then about a week ago or so, a little over a week now I guess, you had this aftershock right in the middle of the aftershock sequence from the previous 2 years. It has the right focal mechanism to be on the interface and also the right depth. So we got interested in this event and we wanted to see how does this compare to the energy distribution we imaged for the 2010 event. And this figure is showing that comparison. So what's being plotted with the red contours, this is the energy distribution for that 2010 event, sub-event 1 near the epicenter, sub-event 2 further to the north. You may notice that these energy distributions are slightly different than what you may have seen in the movie. The reason why is because we were using linear stacking in that movie, whereas now we're more focused on the spatial distribution of energy, so we're using the coherency function approach that I described earlier. So the results don't change that much. We just wanted a sharper image of this rupture for this comparison. So you can see you have sub-event 1, sub-event 2, and then this gridded colored region in the middle, this is the back projection result for the 7.1 event. And you can see it took place right where we saw this jump in the rupture from this 2010 event. So to my knowledge, this is the first time where it can be shown that one of these little details that can only really be imaged using the back projection method actually had strong implications for future seismic hazards, and perhaps it should be used in that way more in the future. Okay, so I'm going to quickly transition to the 2011 magnitude 9 Tohoku earthquake with the little bit of time I have left here. So this is just an overview of the data and source region that the star is the epicenter of this event. We use this large group of stations shown with the red triangles. This includes U.S. array stations, but also Canadian network stations. As you know, thousands of people were killed by this event, and some estimates have slip of up to 60 meters. So now we'll focus in on the actual source region. In terms of the aftershock dimensions, you're talking about 650 kilometers long, so similar to the Chile earthquake, but in terms of the width, it's much wider, almost 350 kilometers. You had vigorous outer rise seismicity for this event, and multiple studies have argued that you have this spatial distinction for this event where the source of high frequency seismic waves were spatially distinct from the actual slip that occurred during the event. So you had the high frequency source down dip and slip up dip. So given the frequency dependent back projection results I've already showed you, this event was just perfect for to study from these multiple different aspects that you can look at using the back projection method.
Hey,
So,
Eric, can I interrupt again real quick?
yes.
Yeah, take as much time as you need to finish. Don't feel rushed. That's the beauty of the webinar.
Okay, well, I will then. Thank you.
Yeah, no problem.
Okay, so I'll just point out that for most of these results I'll be showing for the Tohoku earthquake, we're going to be using the coherency function approach. So the actual amplitude you see on the screen, they don't actually mean anything. They're basically just, they're showing you where the energy release is, but you can't interpret the amplitudes at all. And for this first result, I'll show you data filtered between 0.8 to 2 hertz. So the red star is the epicenter of this event. I should say the yellow line's the Japan Trench. You can see energy starts slightly up dip of the epicenter, or at least strong energy. It then propagates down dip, turns to the southwest very quickly, ruptures to the southwest, kind of stops for a second, ruptures back up dip towards the trench, and then finally back to the northeast at the very last part of the rupture. So I'll let this play again because I just want to point out a few aspects of this rupture to you. I guess the first part is that whenever this rupture transitions from going down dip to the northwest, it's very quick, and in fact you could argue that right there, that's actually a jump in the rupture. You don't see any energy release in a large portion of that southwest movement of the rupture. And if you actually look at the rupture velocities, they're almost P wave speeds. So I think you can argue that that's actually a jump in the rupture there. A second aspect of the rupture I'd like to emphasize is that, at least from this back projection result, this rupture gets closest to the trench almost 2 degrees south of the epicenter and almost 200 seconds after the epicentral time. So I'll just let this finish. Okay. So here's a summary of the rupture. I don't think I mentioned this before, but what's being plotted with the colored dots, these are the centers of the energy kernels at different times during the rupture, with the color of the dot representing the time of the dot. So you go from dark red at the beginning of the rupture to dark blue at the very end of the rupture. So like the Chile event, we can break this rupture up into segments. So you have this initial segment, which with a rupture direction moving down dip, has a very slow rupture velocity of 0.8 kilometers per second. You then have a second section of rupture to the southwest. You have a very fast propagation speed for this southwest propagation of 3.4 kilometers per second. Though these dots are being plotted every 5 seconds, and you notice this huge gap between these two dots in a 5-second time interval. So I think it's a decent interpretation to say that you had a jump in the rupture in this region. The third segment, which moved back up dip, had a rupture velocity of 2.8 kilometers per second, and then finally this later or last segment of the rupture, which ruptured very close to the trench, had a rupture velocity of 2.1 kilometers per second. So that's spatial distributions from the coherency function. You can also look at the amplitude information just to know when you had peak energy release at this frequency range. That's what's being shown here. So you have amplitude on the y-axis versus time. So this is kind of like a relative source time function. And you can see from this plot that the rupture grew very slowly, and you actually peaked out your energy at about 90 to 95 seconds, which on this plot corresponds to this kind of down dip limit of the rupture. Okay, so I'll just take this, in order to make a comparison between this event and the Chile event, I think you could argue that you see a similar jump in the rupture as in this event as you did for the Chile event. It should be noted that no large aftershocks have occurred in this region since the March 2011 event, and that large earthquakes have been produced in this region most recently in the 1930s. So in terms of, I know the technical terms are different between these two locations, but in terms of back projection, this would be a region of perhaps higher seismic potential in the future. So we can also do the same analysis with the frequency dependence as we did with the Chile earthquake. We're going to look at 4 different frequency ranges. The frequency range I just showed you, 0.8 to 2 hertz, 0.25 to 0.5 hertz, 0.1 to 0.2 hertz, and then 0.05 to 0.1 hertz is our lowest frequency that we'll look at. And I'll just kind of quickly summarize these 4 frequency ranges with this plot. So what's being plotted with the black dots, this is the highest frequency back projection result. So you can see that here. With the red, that's slightly lower frequency, so 0.25 to 0.5 hertz. And then going to even lower and lower frequencies, green is 0.1 to 0.2 hertz, and then blue is 0.05 to 0.1 hertz. So what you can see from this plot is that, the first thing you'll see is that you have this systematic up-dip shift in the imaged energy release as you go to lower and lower frequencies. This is very similar to what we saw, but didn't really point out that well for the Chile event, and which others have, I think, pointed out since, that you have this up-dip shift in the lower frequency energy release. I think a basic way of thinking of this is that as you go to shallower and shallower depths, your shear modulus goes down, so it's likely you'll have, I guess, longer rise times for these ruptures that are closer to the trench. A second thing that you can see from this plot is that as you go to lower and lower frequencies, you image more and more energy up dip of the epicenter, so right at the beginning of the rupture. So at this very lowest frequency, you see you've moved, your initial energy is actually pretty far to the east of the epicenter. And the last point I want to make about this frequency dependence actually comes from the amplitude information. So that's what I'm showing here, amplitude versus time. You can see that the relative source time functions for the 4 different frequencies look basically the same, but it's interesting to note that this last episode of rupture, the amplitude becomes larger and larger as you go to lower and lower frequencies, or I should say the relative amplitude does, which may imply, and this I think makes sense, that this rupture very close to the trench may have been somewhat of a slower rupture than the rest of the earthquake. Okay, so I'll just finish this, I guess. So I'm going to just discuss the aftershocks very briefly here. Oops. There we go. So here's a movie of the main shock that I showed you earlier. And if we let this continue to run, you'll see different peaks pop up here. And what these are the aftershocks of the event. And more specifically, some of the larger aftershocks of the event. So we can actually look at these larger events and try to determine the rupture areas of these events. And I should have mentioned here on the the left, I'm just showing you the spatial distribution of all the magnitude 6 or above aftershocks that are in the JMA catalog. So we're going to investigate these larger aftershocks. Here's just a small portion of the aftershock sequence. So this is relative amplitude versus time. So this is kind of like, this is the relative source time function, but now we're not looking at the main shock anymore. Time is with respect to the epicentral time of the main shock. You can see you have these multiple peaks in this relative source time function. These are the aftershocks. What's being plotted with the vertical lines, these are events that are in the JMA catalog, and they're being colored by their magnitude. So red is, these are events greater than or equal to 6, green between 5.5 and 6, and yellow between 5 and 5.5. So you can see, especially for the larger events, typically where there is a peak in our back projection result, there is also an event in the JMA catalog. So, like I said before, we can look at the actual energy distribution, spatial distribution for these larger events, and we've actually done this for events between March 9th and March 7th in this region. And these different contours are the different rupture areas for all of the aftershocks in the JMA catalog with magnitude greater than 6. So you can see you have a variety of different rupture areas for these events. And just for comparison, this red contour, this is the contour of a point source in this region. So you see that the rupture areas we're imaging are actually much larger than our resolution limits, I guess. So one interesting aspect of these rupture areas is that if you only look at the rupture areas that, I guess, contributed to an increase in the cumulative interface failure, so that's just these events here, and you look at the seismicity within those rupture areas, you see a very, I guess, discrete increase in the seismicity only directly following these events. So that's what's being plotted here. This is the average events per hour. On the x-axis is time. So basically I've averaged out the seismicity in each one of these regions for a 48-hour time window around those events, so around those aftershocks. And what you see is within these contours you have very little seismicity before the time of the large aftershock, and then seismicity within the contour that we imaged from back projection increases dramatically and then has this kind of classic decay with time following that. And keep in mind that this is an average of all the events, but you see this same characteristic for events that are on March 11th, but also for events that are on April 7th. You see the same type of behavior. Another interesting aspect of these rupture areas is that if you compare the cumulative rupture area or interface failure by combining the back projection results for the main shock and the back projection result for the aftershocks, and compare that to just the back projection result to the main shock, this is what you see. So the green contour, this is for the main shock plus the aftershocks. The red contour, this is just the main shock from all 4 frequency ranges that we imaged. So you see that you actually increase the total failure of the plate interface pretty dramatically by including these aftershocks. So this is just showing you that. So on the y-axis is cumulative rupture area. On the x-axis, this is time with respect to March 9th. And what you can see is you have this dramatic increase on March 11th of the cumulative rupture area. This inset is just of this blue box here. So you see this is the foreshock. This red line, this represents the main shock, but then you still have the cumulative interface failure grow considerably in the 4.5 hours following this main shock. This growth of the total failure of the interface is quite a bit different than other really large megathrust events in the past 10 years. So the 2004 Sumatra and 2010 Chile events, the aftershock distributions pretty much correspond pretty well to the rupture area of the main shock. So this is kind of a unique aspect of this Japan earthquake. Okay, so just to summarize, for both events we saw rupture segmentation. That's different segments of the rupture with individual propagation directions and velocities. We see jumps in the rupture for both earthquakes. To be honest, I can't tell you how confident we were in the jumps. We were pretty confident in the jumps, but the fact that this large aftershock took place in Chile, right where we had this jump, I think at least should bring about the possibility of exploring these, how these small details of the back projection results can be used as predictors for future aftershocks or earthquakes in a given region. And finally, we saw frequency dependence for both earthquakes. And the common theme between those two is that the lower frequency back projection results, or the lower frequency energy, is always imaged up dip of the higher frequency energy. And then finally, the unique aspect of the Japan earthquake is this total plate interface failure, which I just discussed. So yeah, I'm way over time. I apologize for that, but I'll take any questions you might have.
No problem, Eric. Thanks very much. We don't really have a way to simulate clapping, so I'll just do a little of that. Thanks a lot. That was great. I do have some questions, and yeah, the beauty of the webinar is we can stick around for a little bit of extra time, as much as you have. There are several here. I'm just going to try to go through them in order. There's a couple more philosophical ones that I'll try to save towards the end.
Okay.
The first question I have is from Paul Richards, and he asks, these colors that you show moving around the source region, can you see a way to interpret what the colors represent physically? When you speak of a rupture jump, what is it that's jumping? Is it slip stopping at one place and starting up at another?
Yeah, that's a good question. In terms of what they represent physically, right now, I think the best we can do is comparing the back projection results to two slip models, actually. And it would be, I think it'd be good if more of the information from back projection results were actually incorporated into the slip models, so we could do more of a direct comparison between the two. So my guess at this point is that where we image lower frequency energy is where you have larger slip, but that doesn't necessarily have to be true. It's just some of the comparisons I've made between the different slip models. In terms of
go ahead.
The second part of the question, in terms of the jump, I believe that where you see this jump is basically where the rupture front ceases, and either seismic waves or some kind of dynamic stress change triggers a rupture initiation at a different point. So in general, it's only for the very largest ruptures do the frequencies differ in terms of spatial location. So for all purposes, you could say that's where slip stops and where slip begins, and that jump in the middle is where no slip is occurring.
Okay, great. Thanks. Next question is from Huaijian Yao, and it's about the Tohoku earthquake. For the Tohoku earthquake, do you think the energy released after 160 seconds is related to some of the aftershocks instead of the main shock?
That's a good question. We don't see any. The only discontinuous behavior we see for that event is that jump I talked about during the south west propagation of the rupture. In terms of whenever that rupture turns up dip, I can just bring that up really quick.
Mm-hmm.
I'll just do this. So in terms of when that rupture turns up dip, you'll see that there's no really break in the energy release, I guess. It's all very continuous. So you could argue that that's just a sequence of aftershocks, and that would be very interesting. But from our perspective, we're looking for breaks in the energy distribution, and we just don't see that. So we're interpreting that as a part of the main shock.
Okay. A couple more technical questions. This one's from Januka Atanayake. Have you synthesized seismograms by incorporating your source time function and compared them with observed seismograms? If so, how well do they match?
No, but that's something that we've been thinking about doing for a while. So yeah, you can look at the source time functions at different grid points and then actually use those to generate your own seismograms. Yeah, it's something. That I think is a good idea and can probably actually be incorporated into maybe. Like he says, checking your back projection results. We have looked at this relative source time function that I showed and compared that to the moment release with respect to time. That's, I guess, the closest thing we have done. And the agreement there is variable. It is sometimes we agree very well. I think for the Chile event we agreed pretty well, but for the Japan event, I think that we almost always have peak energy later than what a lot of the, I guess, slip modeling results would show. But yeah, the idea of using the source time functions at different grid points to generate synthetic seismograms is a very good one, and I think, and something that we've thought a lot about.
Okay, sort of on that same topic, Paul Richards has a question on technique. His question is, how important is it to have accurate travel times from each source grid point to each station? Is a simple Earth model adequate? And he gives AK-135 as an example. Is there significant sharpening of the back projection if good empirical travel times are used? And then he says, worked up, for example, from small, well-located aftershocks.
Yeah, another good question. So I would reference Ishii et al. 2007. They looked at this was kind of a later study of the 2004 Sumatra event, and what they did for that, instead of using, so I should back up a little bit. We use an empirical time correction. So we basically force the initial P waves to back project to the epicenter of the event, and that's how we correct for lateral variations in our simple 1D velocity model. However, that's only really correcting, it's correcting for the region around the epicenter, but in terms of how large that region can be and at what point you need to make a different correction, that's I think the heart of this question. So Miyake and Peter Scheer and everybody on that 2007 paper, they actually looked at all of the aftershocks along the rupture of that 2004 event, and they made individual time corrections for the entire length of that event. And they did see that it slightly sharpened the image that you get, but it really wasn't that significant. So I think it can help some. For that particular region, it didn't help that much, and that's why I guess we haven't done it since. But maybe that's an assumption we should make, and maybe we should give more thought into making more of a spatial varying time correction part of the back projection analysis.
Okay. There was another question. This one was from Vera Schulte-Pelcom on looking at accounting for the heterogeneity on the path between the source and the array, especially on the source side where you might get coherent wavefront distortion across the array. Are you accounting for that?
We try to understand it. So I guess one example of that would be depth phases. So we do synthetic tests where we incorporate depth phases and we see how those will influence our results. In general, it will push the energy towards the array that you're using for the back projection analysis, which is, I guess, one really good argument for using multiple arrays in the back projection analysis. But in general, we understand what that shift should be, and we try not to interpret features of the back projection results that fall within that uncertainty that we determine. It's something like 30 kilometers or so is the shift you can expect for that. In terms of a more detailed 3D structure, the only test we've really done for that is to look at smaller aftershocks from the region and see how those are mislocated. Because for a smaller aftershock, basically the energy that you should emit should be right around the epicenter of the event. So any shift away from that epicenter is probably caused by 3D structure there near the source. So it's kind of like this empirical way of testing that. So those are the two approaches we've taken to kind of, we don't eliminate that, we can't correct that information, or at least we don't with this method, but we just try to understand it, basically.
Right. Okay. I have a couple questions more related to the source model. This is a question from Carl Tape. He says, excellent talk, and thanks for the background. I was wondering if you have a synthetic test for some realistic, quote-unquote, kinematic source model for Maule or Tohoku. Take your pick. You showed a nice 3-point synthetic example for Maule, which was the coherency function. I'm wondering what kind of quantification can be used to measure the success of the test. Thanks.
So we have not, for example, taken synthetic seismograms from a kinematic slip model and then back projected those. Other groups have. There's Thornley and that group have looked into this. So the closest we've really came is kind of this empirical approach that I described earlier, where we actually take the waveforms from aftershocks and we will basically set those up as point sources to simulate the same rupture behavior as, say, the 2010 Mali earthquake. So we may have 9 point sources. They're propagating for the initial 45 seconds at a rupture velocity of 2.2 kilometers per second, and then they jump, make this jump, and then propagate at 2.9 kilometers per second later in the rupture. And in that way, you're kind of incorporating some of the structure within the region into that synthetic test. And I guess the success there is to just basically say, did we image the locations and times of the point sources with the accurate amplitude information if you're doing linear stacking. So I hope that, yeah, that's about as close as we came to doing what you're suggesting, I think.
Okay. I have another question from Huaijian Yao. This is involves comparing to the slip inversion results which have been produced for this. He says that most of those results show a dominant slip north of the hypocenter. Why is there little energy ruptured in the northern, or I'm sorry, little energy radiated in the northern part of the rupture area for the Tohoku earthquake, even in the low frequency band, which was 0.05 to zero point 0.1 hertz?
It's possible. So let's go on the assumption that there definitely is slip north of the epicenter, co-seismic slip. It's possible that the frequency ranges that we're looking at just aren't low enough to really image that. To do that, we would have to, I think, turn to S waves or even surface waves, and to really confirm whether or not we could see that kind of rupture behavior go to very low frequencies. So I would say it comes back to this frequency dependence.
Okay. And another question from William Harbert. This was, can you estimate stress drop and also visualize that?
Yeah, I believe possibly we can. So if you look at the rupture areas of, well, okay, I guess I'll start, yeah. So if you look at the rupture area of the Tohoku event, and then you use the moment magnitude as estimated from other methods, surface waves or normal modes or whatever, then you can estimate the stress drop, assuming some, from that you can stress drop, yeah. So that's in the paper we wrote on the Tohoku event. I think we estimated something like 70 bars for this event, based upon those two values.
Okay. Last question is from Paul Richards, and he's asking, the practical examples of back projection that I've seen use data from dense networks that cover only a narrow range of distance and azimuth from the source. Why isn't it better to work with stations all around in azimuth and all within a simple mantle window in distance?
I mean, the main reason is that if you would look at the waveforms, they would not be as coherent from a large azimuth range. So that would produce artifacts after you stack those seismograms. Yeah, I think another problem, which goes back to this coherency, is that the directivity effect on a very large range of azimuths can kind of distort your waveforms and cause some problems during the stacking process as well. So it just, yeah, I guess coherency of waveforms is the real problem there. That's why you want to kind of keep it to array data. Though you can use two different arrays, so the coherency of waveforms within one array will be similar to the coherency in a second array. You stack those together, and then you combine the stacks, because presumably once you generate the stacks, you've eliminated all this structure information, and then you're just combining the kind of the relative source time functions together. So I would say that's the best approach, is just combining arrays.
Okay, great. I guess I had a follow-on question to that, thinking about if there's any resolution to be gained from tighter station spacing. Is what's available out there now ideal, or have you thought about looking at maybe a couple Pascal experiments that were out at the times of one of these earthquakes that might have had tighter station spacing? Would there be an improvement in resolution from that?
Yeah, I guess you want, I mean, the more data you have, the better, but I think it's really the azimuth and distance. So it's basically the aperture of your array that matters. So even if you have a very dense array, if it doesn't cover a large region, then it's not going to do much good, actually.
Okay. All right, great. Well, I think that's all the questions we have. We got another comment from William Harvard. He said, "Interesting. Thank you. This was wonderful." Yeah, I think this was really great, Eric. Thank you very much for your ability to do this.
Yeah, no problem. And yeah, thank you to all of you who took the time. And once again, thank you to Iris for inviting me.
Yeah, our pleasure. And I just wanted to say, everyone who's still out there, yeah, thank you very much. And we've been recording this, and we'll make it available online. We're putting together a website to archive and distribute all of the webinars that have occurred so far. So if you or one of your colleagues who might have missed this is interested in seeing it later, we'll have it available. And yeah, with that, I'll wish everyone a good day. Thanks again, Eric. Thanks Vera as our TOG chair.
All right, yeah, thank you, and yeah, have a good day.
All right, goodbye, everybody.
All right.